All right, we will get back to that. That was not it reminding me to turn on the recorder. It was that thing involving the shirt and piece of that all this gear is. So we're going to talk about data types and typecasting. We'll refresh our memories of what integers, floats, and strings are, because you had that in the last lab. At least introduce you to what Booleans are. And we'll look at a few string functions and operations. Go through how to build a notebook in a little bit more detail. Not a lot, and that will probably take us to the end of our time together this morning. I need to check one thing. Be sure that the microphone's picking me up. It looks like it is. And I have a feeling I'm going to have to demonstrate stuff. So let me get a working notebook going. Deployments. Get to the correct class, although I actually deleted at the end of class. So I think last time I used Untitled 1, I'm just going to reuse it. So that was our last lesson from last time. All right. So data types. So in the computer, data are all binary digits. They're actually 0 and +5 volts usually. At a higher level of abstraction, the data are typed into integers, real or alphanumeric representations. And there's a few other types that appear from time to time. The type impacts the kind of arithmetic that you can do on a particular value. That's all it really, that's the big take-home message. So if you're expecting to perform integer arithmetic and one of the participants in the arithmetic happens to be a real variable, it won't work correctly. Similarly, if you're expecting to perform string operations, manipulating characters, so A through Z, 0 through 9 as characters, and the variable is not a string type of variable, your manipulation will not work correctly. It may run, you may not get the pink rectangle of encouragement, but it won't be correctly. So being aware of type is fairly important. It's usually not a deal killer, but it is something that you need to always have working in the back of your mind if you're trying to maintain and repair your script or somebody else's script, or purchase scripting services from somebody that's selling them to you. A common and really difficult to detect source of errors that tend to snowball as your program proceeds is mixed mode arithmetic. And I think we did that, I think Josh did that in lab for you last time. We'll revisit it here. So the programming kernel is capable of doing mixed mode arithmetic, which means that if there's a real variable, an integer variable in an arithmetic operation, you can usually resolve that and come up with a result. But every time it has to take an integer, which is infinite precision, and convert it to a real to perform some arithmetic, it introduces a little bit of error. It's called truncation error. A little bit of error doesn't matter very much, but let's suppose we have our Python script that's flying our ship to Mars. We're all in the ship together on our way to Mars. We won't make it because we'll end up killing each other, but that's beside the point. We got our big ship to Mars, just like the movie Passengers, except our sleeping pods didn't work, so we all have to entertain ourselves with the automated bartender and hope that there was enough supply on board to get us for our, I think it's supposed to be 8 or 9 months if we can do constant acceleration to the Lagrange point between Earth and Mars, and a constant deceleration to get there. Okay, so our program is flying the ship for us, because that's way too important for a human to be left to a human being. We're busy getting drunk at the bar, right? Come on, at least some pseudo grins for the back. Yeah, like you've never had an adult beverage in your life, please. And our program has integer and real arithmetic in it. So every time it does something, it's getting a little teeny bit of error. So Mars is about 8/10 of the diameter of Earth. So you figure if we leave from Earth and we're pointing right at it, everything's happy, we're good, and we can handle some angular deflection. But if we get like a 1/100th% error every calculation, by the time we get to where Mars is supposed to be, we've missed it by more than miles. We've missed it by half a parsec, and we're headed on into Jupiter. We get caught in the gravity well, and you know what happens then? Well, it's time for a commercial in my space odyssey, but we get spin around and game over. So truncation error is something that's real and important in a lot of scientific computation. It matters a little bit here, but we're not going to make that big deal of it in this class. So what are integers? Well, if you can read, they are numbers without any fractional portion. So nothing after the decimal point, which is not used in integers. So numbers like -3, -2, -1, 0, 1, 2, 200 are examples of integers. How about pi? Is pi an integer? That'd be a no. Good. Yeah, it's one of them transcendental meditation numbers. To declare an integer in Python, you just point to it. You just have a variable name and you assign to it the integer constant. So as an example here, my phone number 14158576309. I hope that's 10 digits. That act will make the contents of the variable named my phone number an integer. We can test that conjecture simply by copying that, or we could type it, but we'll just do copy paste. And I guess I'll leave all that stuff up there. So I go ahead and put my phone number in, nothing happens. How do I find out what type of variable that is? Keyword type. And I just put in the variable name. By the way, that's not really my phone number, so call it if you want. It might be the corporate headquarters of Denny, but I think that's 1-800-EAT. So it's returning an integer. And if we were to wrap that in a print function, which would probably be the more useful way to do this in our programs, throw print around it. It's the class of integer. Okay, so no great revelation there. Our next kind of number are real as opposed to fake ones, also called floats or floating point numbers, because the decimal point position is allowed to float based largely on how we choose to represent it. So right there, it's just represented as a number with a decimal point, but we can choose a scientific notation where it would be represented as a mantissa and an exponent. We can change the base from base 10 to base 2. Still have mantissa and exponent, but then we'd have to be able to be smart enough to interpret what base 2 exponents are in humanly understandable numbers. So numbers like 3.14159 minus 0.001, 11.11, and 1 decimal point, those are all examples of real numbers or floats. The key thing is that they have a fractional portion to the number. So 3.14159 is bigger than 3 and smaller than 4, the next integer. So it has a fractional portion, and that's pretty close in decimal value to that number pi that we already established is not an integer. So if I was to take my mass in kilograms 74.84, and that actually is pretty close to my mass in kilograms. And we will steal that because we're going to need it. Copy that, paste. Any guesses what will come up? Have like a less than sign. It'll have a keyword class. Have a single quote. What are the next three characters most likely to be? 2, 3, 4 characters. 5. Good. You are right. I hope. That was close. Embarrassing for everybody involved. Next one, strings. So a string is a data type that to us, we interpret as text elements. The usual letters themselves are characters and strings. The numerals 0 through 9, if they're part of a string variable, are just characters. The underscore, actually any ASCII character can be in a string, and there's a bunch of them. There are also extra bonus features of hidden characters. So strings are a pretty flexible critter, except when you want to do arithmetic on them, in which case you spend a lot of time in the pink box of figuring out what the heck's wrong. So let me just copy all those, and I will declare my name, my cat's name. Okay, so those three are now, pretty sure those are string variables. By the way, the cat that's on the screen, when I boot up, what do you think its name is? Good guess. I have at least 3 cats, so you had a 1 in 3 chance of being correct, and you nailed it. So if you're going to Las Vegas this weekend, good luck to you. And so now let's find out that indeed those are strings. See, we'll do my name first, which happens to be enclosed in single quotes. Yep, it's an str, which is string, and then we'll do my cat's name, which you'll notice is in double quotes. So there's not a lot of functional difference between single and double quotes. It tends to make it easier to read scripts sometimes. And if you're in older versions of Python 2.7 and earlier, there is a slight functional difference, but you can't interchange them. So if we put my cat name, double quote, the characters Dusty, and then single quote, it wouldn't formulate it correctly. I actually don't know what the error would be. However, we can figure that out real quick. Oh, I bet my editor won't even. Okay, so if I mix the quoteness, it can't scan the literal correctly. What it's doing when it's trying to create the string Dusty to put into my cat's name is it sees that first double quotes, and that's telling the kernel, okay, everything in this first double quote to the next time I see a double quote is to be rendered as a character. So it has a code for a capital D, it has a code for a lowercase u, and so on. So it's trying to convert all that into characters. And when it gets to the end of this line, it encounters an invisible character, which is the carriage return line feed character. We can see what those look like in a different kind of editor. It never found that second double quote, so it's basically saying, what WTF, what do you want me to do? And so we have to provide the resolution. Our choices are, we can single quote that, and that should run just fine, or we could have double quoted the second one. I make that mistake a lot when I'm hurriedly trying to do a new script for something stupid, so expect it to happen from time to time. It's not a big deal. Just go fix the quotes and proceed forward. So all those are strings variables. They can be combined with one another using concatenation. And the symbol for that is simply the plus sign. I bet you there's a concat function, but I'm not going to go looking for it. And if you're doing a bash shell script, it's cat, C-A-T, cat. And what concatenation does is it takes the contents of one string, contents of another string, and joins them. No space between them. So if you want the space between them, you have to provide it in one of the other string or somewhere in the intermediate. Concatenation, really handy tool if you're having your script go out to the internet and get a file from somewhere. Because that way you can get the path to the file. And if there's individual files in that path, you can change the file name quite easily with concatenation. We'll see examples of that, not today, but coming up pretty soon. Here's a collection of a bunch of different variable types just to illustrate them. So we've got phone number, mass in kilos, names, cat's name, and the cat's mass in kilos. And now we're writing a story called All About Me. And so the next line, I'll return my name, my mass in kilos, my phone number, and then my cat's name. And you'll see that right there is the backslash is something called an escape character. And it allows us to put the single quote there without buggering up our string. So the escape character makes the character just after it treated as just a character. So the kernel no longer interprets that quote just before the I in my cat's name as a delimiter for the end of a string. And there are other ways to accomplish the same goal. In my mind, this is by far the easiest. Put in the escape character and you're good to go. And then we have something all about concatenation. I'll take my cat's name, my cat's mass, and call it a silly string, all lowercase, and then we'll do it again, but we'll convert it to uppercase. So I don't need to run that. This is what the output looks like. So the upper and lower function are pretty handy. So if you have a string and you decide you want it all uppercase, you can postpend the string with the dot upper function. There's also a dot lower function to make every character lowercase. This dot in the syntax is fairly common in any Python scripts you'll encounter. In this instance, the dot, the string itself, doesn't matter what the letters are there. So the thing between those single quotes is the string. The string is a member of a class of variables called string classes. And those classes happen to have a method associated with them named upper. So if you identify the variable, it automatically inherits the property of class. And so the dot upper function is automatically available if the variable exists. And we'll see this dot syntax a lot. It's just part of this particular language. We can also format strings using a % operator or the format function. I think the concepts are introduced later in a different workbook. Or you can Google search for examples on how to do such formatting. So our next variable type of some significance is called Boolean. I guess there was somebody named Boole, or maybe it's just a joke on all of us, and I'm not in on the joke. But it's also called a logical variable in other contexts. And so it's a data type which represents one of two values. It can either be true or false. Actually, it has three. It can be true, false, or null. Null means it doesn't know what it is. True is true and false is false. And it's generally used to represent truth values of expressions where we're making logical decisions. And it's actually fairly important because we use true or false as one of the main program control structures called selection. So we can select one thing to happen based on whether something's true, something different if it's false. And I guess you could conceivably do something even different if it's null, but I think things just come screeching to a halt. So here's a couple of examples. Here I have a numeral 1, and when that gets executed, that becomes the constant named 1, and it happens to be an integer. I can equate it to itself using the double equal sign operator, and the result of that operation is a Boolean variable as yet unnamed. It happens to be true. Similarly, the constant 2 less than the constant 1 is a false conjecture, and when it's executed, it produces a Boolean output called false. We can get the type of the result. Here we have 1 equals 1, and it returns bool, which is Boolean. So let's play a little bit of this game with that. So if I do that, I get true back, but there's no particular variable named with that. I'm pretty sure somebody come up with an interesting short name. Yeti it is. Good thing you had that sticker on your computer. So we will declare Yeti is equal, I think this assignment will work, or there's two possibilities it's going to happen. It's going to work the way I want it, and Yeti will take on the properties of a Boolean variable, or yeah, pink box of encouragement. In the afternoon class, it was declared the pink box of loser. So they make more value judgments on themselves. Okay, so cool. That's what I wanted to have happen. If I type Yeti, there you go. Abominable snowman is a Boolean. And we kick the cables just to keep the connection alive. Something could be solved with a few inches of duct tape in a matter of seconds, except that it's locked because everybody knows that the faculty can steal stuff out of a classroom. We won't. We have better shit in our office. All right. Well, that's all getting recorded. I said I have a better shirt in my office. You misunderstood that, recording world. So moving on. Here's some more examples of Boolean. So first thing is, it's somewhat easier to mentally understand if we actually assign the true or false value to a named variable. So here I'm setting double x equal to true. The act of making double x equal to true makes double x, the variable name, a Boolean or a logical variable. I chose two x's because that's the double cross, and that's what happens when you're doing truth and falsity. You get double crossed at some point. So now we'll just play some games with logical variables. If we set a variable single x to 5 and y equals to 10, we can have it print the Boolean result of x identically equal to y. So the twin equal sign is simply asking the question, is the contents of x identically equal to the contents of y? So for that to evaluate as true, x and y have to be the same data type. So they both have to be integers, floats, whatever. And their value has to be the same. So if we set x equal to 10 decimal point, we'll do that in a second, and y equal to 10, I'm pretty sure the result would be false. False is x is not equal to that first one. So I'm reusing the variable x a lot. Next thing we can do is we can set x equal to a null value, which is none in this case, and print its contents, and we'll find out that it returns false because false and none are treated the same as far as a Boolean evaluation. We can set it as an empty, let's see, it's not an empty sequence. That's called it, that would be an empty tuple right there. We'll see what a tuple is coming up soon. Not today, but next week. That's also empty, and so it's going to return false, and so on. So all the results are right are here. If we set x equal to kitty cat, any non-empty string by default is treated as true. So if you have a string and it's empty, there's nothing in it, that'll evaluate as false. Once it has something in it, it evaluates as true. Off the top of my head, I don't know the utility of that, but it wouldn't be there if there wasn't good reason. So I wanted to play with this one real quick. I'm not going to grab them all. Copy that. Let's play a game. How about global thermonuclear war? How about a nice game of chess? Okay, so here we have. It's just really, I'm now starting to get annoyed. All right, so here we have our variable named x, which I've set as 10 point, and a variable named y, which is 10. At first glance, if we were to test, does 10 equals 10? We go, yeah, sure, of course they are. It's the same thing. But x and y at this moment, once I run that, are different types of data. One's a float, one's an integer. And so they are not identically equal. Do not embarrass the machine. Work the way I'm expecting you to. I stand corrected. I also stand confused. You have made me mad, so. I retract my prior statement. It's converting the 10 point and the 10 into some sort of equivalent representation, comparing them numerically. So 10 point and 10 are indeed the same number as we think they are. That confuses me. Let's just see if that's a property of 10ness. So it converts it probably converts the y into a float, makes the comparison, and returns the result. So I didn't expect that. I thought that should have turned out false. So be it, I make mistakes too. Fortunately, I'm the instructor, so I grade myself, so I did great today anyway. Moving on, numbers can be used as Boolean values by using the built-in method. Any integer, floating point number, or complex number having 0 as a value is treated as a false. Well, if they have any value other than 0, then it's treated as a true. And that does have practical application in some complicated programs. But sometimes you have a complicated program that you're trying to run. And rather than have to exit and convert positives or negatives and zeros to Boolean variables, you can just treat them as numbers and it takes care of it for you. So that's used for flagging things and counting. Boolean operations themselves are just simple arithmetic of true and false, and they can be manipulated using the and, or, and not operator. So the actual words can be used. If you look on the Google it, they'll give you word examples. There are also character examples for, I don't know what the one is for anymore, but not is the exclamation point symbol. So you keyword or, and it's exclusive or. So if one's true, the other one's false, that will evaluate as true. If they're both true, it'll evaluate as true. If they're both false, that's the only way the or will evaluate as false. The and is inclusive and, so both things have to be at the same logical result. So So false and false evaluates as true. True and true evaluates as true. True and false evaluates as false. And then not is the circle slash of programming. We can change types from one type to another as long as it makes some sort of sense. That activity is called typecasting. If you go read, Python for Real Beginners or Python for Idiots, which is what all my stuff is based on, there's an entire chapter on typecasting. Apparently, it's a fairly big deal. There's 3 functions that allow it. There's the integer function, the float, and the string function. We've all actually seen the Boolean function independently. And so if we supply to the integer function a representation that can be an integer, it'll convert us to an integer, treat it as that. So ABC can't be converted to an integer, but the character string 1, 2, 3 can quite easily be converted to an integer. And there are similar conversions for other things. Almost anything can be made to a string. And then a float plays the same role. There's also the type function, which we're familiar with, which tells you the type of the variable. So here we have an example, a variable named s, which contains the string 1, 2, 3, I am a cat. And if we print the type of it, it will tell us that it's a string. And we can convert the first 3. We can take the first 3 characters of s, convert it to an integer, and then return it, and we will get the type as an integer. And let's go see what that does. Okay, so we have, I'm a cat. I'm going to attempt to convert I'm a cat, 1, 2, 3, I'm a cat into an integer. So there's only 4 lines of script there. And I have a note to myself, this should generate an error. So what's the error it's going to generate? It'll be pink screen of death, that's okay. The 1, 2, 3 is representable as an integer, but my kernel doesn't know how to represent capital I, lowercase am, capital A, lowercase cat as an integer. And sure enough, I get a message that tells me that, and it tells me where I made the mistake, and that gives me an opportunity to try to fix it. So being fundamentally lazy, the easiest way to fix mistakes is just comment them out. If I do that and run it, I know that that screen is currently I just commented out the type conversion, and I have string and string. Actually, let me modify this a little bit. So I'll print the type of it after another type conversion, and I'll actually print the contents. We can extract characters from the string that happen to be numeric. And in this case, the characters in positions 0, 1, and 2, which are 1, 2, and 3, are indeed representable as numbers. And so we can get a numeric output from that. And lo and behold, oh, that's right. I forget how it counts. So there we go. So now we've grabbed the first 3 characters. Remember, Python starts counting at 0, and it causes things like this to happen. You forget that it stops before it gets to the next one. And so now we have successfully typecast a substring of the original string as an integer. And that's something that gets done a lot. Here's some more examples. I'll let you just look at it briefly. And let me check what time it is. Damn, I'm talkative today. I didn't even ask anyone for questions. So quickly, in the next 6 minutes, we'll go through some guidance on how to program a notebook. Are there any questions before I go to this course? I think it's fairly straightforward. I know it was covered a little bit in lab last time. Obviously, you get more of it today. Hopefully, by the end of today's lab, you will be sick of strings and type conversions, which is our goal, because that means that you have had it repeated enough that it is kind of second nature. So if you recall the problem-solving protocol from last time and the time before and the time before, state the problem, list the input information, governing equations or principles, and the required output, create a sample problem that you know the answer to, because you can use that to test your general solution, come up with a scheme of general solutions, so sort of create an algorithm. You could just write it down in English-looking words, convert that into something your computer can manage, test it against your by hand example. You should get the same example, it's the same answer unless you mess something up in the computer program, assuming you didn't mess it up in the by hand example. And then finally, refine it for any deployment. So if you want to make it reusable, you can do some subtle modifications to handle that. If we wanted to go in a deeper sense, and we were in Cal Poly in their computer science program, they have a whole web page on how to build a program. And it's high level like this. It doesn't actually tell you how to do anything useful. So the first part is to understand the requirements. That's what I have called listing the knowns, the unknowns, and the governing principles and the desired output. Then create a test plan. That's the by hand solution. Then invent a solution. The author of this at Cal Poly has a very good opinion of himself and students. I'm fine with stealing a solution. That's just as good as inventing it. There's a reason that Russian and Chinese go-fast airplanes look almost like US go-fast airplanes. Part of it's the physics, and part of it is we're not going to invent this stuff, we'll just copy theirs. It's a whole lot easier. And that is encouraged, at least in my class, with one special caveat. You have to tell me who you stole it from. And on a test, you're not allowed to steal from each other or any other living thing, living human. If you can have a seance with a dog, it helps, that's fine. No living human. So inventing a solution, copying someone else's and modifying it to fit the problem is perfectly legitimate engineering behavior. And that's how the whole engineering business works, is you would borrow already solved solutions to fit your problem. Or to put it kind of more crudely, there's no point in reinventing a wheel. If someone's already invented a wheel, and all you need to do is change the diameter to make it fit your problem. Change the diameter, move on. You got more important problems to deal with. Next, you want to design or formalize your solution. That's kind of creating the architecture. I would call that the flow chart or the pseudocode. And then you convert it into something a computer can run it, you test it, and then you're good to go. So here's a really quick example in 4 minutes or less. Let's suppose we were presented with the general engineering problem of how to get out of this gravity well that we've just fallen in that the light can't escape. We made it. We have an engineering material problem. We want to build an okay, that's spooky. We want to build an automated classifier that will tell us if our material has been loaded in the elastic or inelastic range. Suspend for the moment why you would want a computer to do that, because oftentimes with real materials, you can tell just by looking. And so here is the loading situation we're going to do. We're going to take this material and we're going to pull on it on each end. What's going to happen to it? And this is how wire was invented. It took a perfectly good piece of steel and pulled on it. Before you knew it, you had wire. It's going to deform. As drawn there, you would expect it to get longer. The stress is the force divided by the cross-sectional area of the object. So if we pull on something hard enough, it deforms, and when we let go of the load, it stays deformed. That is the right picture. That's the inelastic condition. But if we pull on it, not so hard to cause permanent deformation, when we let go, what happens? It springs back and hits us in the butt. That is the elastic condition. So that's all we want to test for. So for some reason, we want to classify whether it's loaded in the elastic or inelastic region, and we don't want to think about it ourselves. The yield stress in this case is the classifier. And once the material yields, it begins to fail. It won't carry an additional load. So let's follow a problem-solving protocol. Our first step would be to state our problem. Our problem is to compute the material stress under an applied load, determine if the value exceeds the yield stress, and report the loading condition. That's literally all that picture summarized into a single sentence. Our next step is to identify the inputs, governing principles, and outputs. Inputs are easy: applied load, cross-sectional area, and the yield stress for the material that we get out of a table of yield stresses. Or actually, no, this is modern times. We don't have to use a table of yield stresses. We use the mighty, begins with the letter G, needs the internet to work. If you want to know the yield stress of aluminum, how would you find it? Yeah, thank you. Google it. Or Bing Bong it, or Yahoo, or whatever's left on the search. I think Ask Jeeves is the fun. There are a few other search engines. Frankly, just use Google. They own the internet world of this kind of stuff. Our governing principles are that stress is force divided by area. And when that value is less than the yield stress, then we are in the elastic region. When it's equal to or greater, we're in the inelastic region. That's all we need to know. And the outputs, we might as well report the stress back and what the classification is. And then we work example problem by hand. So this is not the highest level of arithmetic we could imagine. Let's assume we have a material whose yield stress is 1,000,000 pounds per square inch, and the units would matter in an actual case. So whether it's in pounds per square inch or SI equivalent would matter. So if we applied 10,000 pounds force, cross-sectional area is a square inch, our stress is 10,000 pounds per square inch, that's elastic by our information. Same for 10,000 and 1/10 of an inch, we're still elastic. If we apply 100,000 pounds on a 1/10 of an inch diameter rod, we get 1,000,000 pounds per square inch of stress, which is way beyond our yield stress. No, it's equal to our yield stress. We would declare that inelastic. And nobody here knows anything about stress and strain, right? And you don't need to. That's the cool thing about it. You could be a congressman right now. You don't need to know about stress or strain. So the stress requires us to read in the load value, read in the cross-sectional area, divide the load by area, and compare the results to yield stress. If it exceeds the yield stress, then the actual stress is the yield stress and the loading is inelastic. Otherwise, it's elastic. So there is our formula, and there is our condition that we use to test. And so this condition will be in what kind of structure? Begins with the letter B. Boolean, good. And so here's a flow chart for the problem, kind of overly pedantic flow chart. So we read in a value for P, A, Y, we compute the stress. We ask the question, is stress bigger than yield? If the answer is yes, inelastic, stop. If the answer is no, we report elastic, and then we return the value, and we stop. And the next step would be to code the algorithm and test it with the by hand data. So here's an example with the yield stress of 1,000,000, applied load of 10,000, cross section of 1/10. And here is the conditional. So if the computed stress is less than yield stress, we're going to print that. Alternatively, if the computed stress is greater than or equal to stress, the yield stress, we print that value, and there it is applied as an example. And then the next step would be to test it with the other two cases, convince ourselves it's working as expected, and now we're ready to use it. So this has a notation. We'll go ahead and copy and run this. So on my instructor notes, I can't have interactive stuff because it breaks things. So I just code them as copy paste stuff. Except if I don't do it right. And then we will end and get ready for lab. Okay, so the interactive stuff, which we don't learn today, it's coming up in the class feed. So now it's asking us to provide values for our inputs. So let's say we have a material that has a yield stress. Somebody pick a number. That is a wimpy material. Thank you very much. Let's apply a load to it. 350. And cross-sectional area in square inches. I'm pretty sure this will be elastic. Oh, I'm wrong. I'm a fool. So we're in the inelastic region. And if we had to do that over and over again with different materials, we now have a classifier, and we would easily be able to determine whether we're loading something in the elastic or inelastic region. That, I believe, concludes today's lesson. So I will go back to my office and get the phone call for lab 3 set up. And is there a class in this room afterwards? Doesn't seem to be anybody waiting out there. I will look into we'll stay here for that. Oh, there is another class out there. So it's take me about 5 or 10 minutes to set it up. It should be the same link as before, but I again will send an email to everybody, so expect that. Okay. Original ENGR. I'm just gonna have to remember that because I got to get the phone call started. In the chat box in the lab, Ben, go ahead and remind me that you just came late, and that way I can get it fixed up. Actually run them, so you have to turn the comment off. So, yeah. Run the cell. And then it's giving you an error because you haven't defined the ABC yet. Okay. That's all of that. Are your lectures like yeah. Okay. Stop share.